Welcome back, Physical Science 20. So this is the second part of FC2. So molar mass. Calculate the molar mass of various molecular and ionic compounds, and then perform molar mass conversions, including mass to mole and mole to mass using the correct number of sig figs. So molar mass. Hydrogen is an important industrial chemical. And the most common production method is by the reaction of a hydrocarbon with steam, i.e. H2O. So what happens here, the carbon and the hydrogen switch places, we get the production of hydrogen gas and carbon monoxide. The chemical equation tells us that we need 1 molecule of water for every 1 molecule of methane. Hydrogen manufacturers must have a convenient method of measuring exactly those amounts. Simply combining identical masses, so if I had 10 grams and 10 grams, that doesn't work because the atomic masses of carbon, hydrogen, and oxygen are all different. Therefore, 1 kilogram of methane and 1 kilogram of water won't work because they have different numbers of molecules. So remember, it'd be like saying if I have a dozen, or if I have 2 grams of basketballs and 2 grams of golf balls, I have different amounts of them. So to get around, and again, we have to know the exact amounts that we need. So to get around this problem, chemical manufacturers calculate the amount of substances required. To do this, they determine the molar mass of each substance. The molar mass is the mass of a mole. So the mass of 6.02 times 10 to the 23rd entities, whether it's atoms, molecules, or formula units that we have. The units for molar mass are grams per mole because we're talking about a gram in 1 mole. Chemists often use the symbol big N to represent molar mass, with the chemical symbol or formula as a subscript. The symbol for molar mass of water we would say is big M with H2O, indicating I'm figuring out the molar mass of H2O. Molar mass of elements, the molar mass of a monatomic element, such as neon, is just simply equal to the mass on the periodic table. And we'll see why that works in a second. So neon, the mass number 20.18, that would be the molar mass of that. The molar mass of a molecular compound such as oxygen is determined by multiplying the molar mass by the number of atoms or molecules. So for neon, we could just simply say, okay, the molar mass of neon, so I use a big M to demonstrate molar mass. Neon is just simply 20.18 grams per mole. And what I'm doing there is I'm just rounding off to 2 decimal places, which I recommend you do. So 20.180, just simply round it off to be 20.18. All right, if I look at the next page, I'm looking at oxygen. It's a diatomic gas. So the molar mass of oxygen. We, of course, know that there's 2 oxygen. For every 1 mole of oxygen I have, there's 2 moles of actual elemental oxygen. So oxygen is 15.999. So we can just round it off to be 16.0, and we get 32.0 grams per mole. If I'm looking at the molar mass of phosphorus, one way that phosphorus comes is 4 phosphorus atoms joined together. So if I took not 1 atom, but a mole of those, 6.02 times 10 to the 23rd of them, for every 1 mole of phosphorus, I actually have 4 phosphorus atoms. So phosphorus, of course, is 30.97. So it's going to give us 123.88 grams per mole. All right. So yeah, the mole represents a huge amount, 6.02 times 10 to the 23rd. And before we start this next paragraph here, let's just take a look at this. So if you had a bunch of random substances, and if you didn't have a balance and you wanted to figure out how many times the larger ones were than the smaller ones, you'd likely set your lightest object as being 1. Just similarly to what the periodic table has. Hydrogen is very close to 1. Okay? And then if we look at carbon, carbon is 12. So we know that a carbon atom is 12 times more massive than a hydrogen. So those are called atomic mass units. If hydrogen has 1 atomic mass unit, we know that oxygen is about 16 times larger because it has an atomic mass unit of 15.999, etc. Now, what the mole does, if I take a certain number of atoms and throw them on the balance, so let's say I pick carbon. If I pick a certain number of atoms of carbon and throw them on a balance, it would be nice to figure out the number I would need so that it would read 12.011 grams. And that just happens to be what the mole is. So if we take a look over here, numerical equivalency of atomic numbers and molar masses, the mass of 1 mole of a monatomic element expressed in grams per mole has the same value, the same number as the average atomic mass of the element expressed in, quite often we use a little u for units or AMU. That would be convenient. This means that on the periodic table, you just have to look at the only mass value needed. This means that on the periodic table, only 1 mass value need to be given for each element. This is true because the value of Avogadro's constant. We can use carbon to illustrate that. So according to the periodic table, 1 carbon atom has an atomic mass of 12.01 units, right? So 12.011 times larger than a hydrogen. And chemists often define 1 unit as the following. So if we rationale that 1 unit could be 1 proton or 1 neutron. So those are approximately equal in value. Electrons are really, really small, much smaller than that. So an atomic mass unit is 1 proton and 1 neutron. And of course, if I look at carbon on the periodic table, we see that up to the left here, we have the 6, indicating 6 protons and 6 neutrons. So that's what the atomic number represents. In this case, it also represents 6 electrons. So for protons, I like to call them P positive. Neutrons are neutral, so they're N negative, and electrons are E minus. So the 6 here tells us that there's 6 protons and 6 electrons. And we have a mass of 12.11. And loosely speaking, to get that total mass, as I mentioned, if I'm looking at carbon, most of the mass is in the nucleus. So we have our 6 electrons going around, right? But most of the mass is in the nucleus. So in this case, our protons and neutrons. And of course, we have 6 P's and 6 N's to make a total of 12 units. So if we take a look, if 1 unit represents this many grams, which was experimentally been determined, starting off at the charge to mass experiment, the mass of 1 carbon atoms in grams, therefore, is, so if 1 unit represents this many grams, our carbon, which has 6 protons and 6 neutrons, if I multiply that out, I get this many G's. So that's the mass of 1 atom. Mass of 1 carbon atom. And of course, if I take not just one of those atoms, not 100, but if I take 6.02 times 10 to the 23rd of those atoms, so if 1 atom is that, multiply that by that number, and lo and behold, look what we get. 12.01 grams. So this is what's so special about that number. If I take that many of any atom on the periodic table and put it on a balance, the balance would read these numbers here, which represent grams in every 1 mole. So the mass of a mole is what that turns out to be. So that's really, really handy. So what we'll do is we'll stop the video there, and then we'll come back with part 2 and then look at some more molar mass calculations, then doing some conversions.